Okay, now we're going to look at calculating areas maybe between more than two curves or just some unique spaces and the different ways we can kind of picture that area being calculated. So we're going to see the area that's shown highlighted that's between the curve y equals square root of x, y equals x minus 2, and the x-axis. So we really kind of have three lines that are entrapping this area. And we can see that the two curves intersect, the two graphs other than the x-axis, they intersect at the point 4, 2. So how could we do this? Well, we really are between two curves for half of this region and two other curves for the other half. If we kind of segment our area like that, we can see that we have a region on the left and a region on the right, and in total, if we did this area, we would first start with the integral from 0 to 2 underneath the square root of x graph, because that goes all the way down to the x-axis, so that's just the integral of the square root of x. And to that, we would add the integral now from 2 to 4 of, now it's between two lines, not the x-axis, and so we would subtract them. The one up top is square root of x, and the one on the bottom, which we would subtract, is x minus 2, and all of that is with respect to x. So we could calculate that out, and it would show us that our area is equal to 10 thirds units squared. Okay? Let's consider this area a little bit differently. So imagine that we have our graph we were just looking at, where this is the x-axis and this is the y-axis. Imagine that we rotated this picture 90 degrees counterclockwise, okay? And now we're looking at our picture like we are on the right, where the y-axis is now down here and the x-axis is going vertically. So what if we considered integrating this with respect to y? Well, now we could do this in between just two curves, where we have a curve up top and a curve on the bottom, and we're going to integrate little rectangles going that direction. Okay? So again, this point over here is the point where it's still going to be x is 4, y is 2. Okay? And now I want to consider these functions not in y equals form, but it's nicer to have them in x equals form if we're going to integrate with respect to the y-axis. So this function would actually be x equals y plus 2, and our square root function is really going to be, if we square both sides, we get x equals y squared. I have to squeeze this in over here. X equals y squared. Only the left-hand side of that function, obviously. And so now, how would we integrate with respect to y? Well, our area would be equal to, now we want to look at the boundaries on the y-axis, and that would go from 0 all the way up to that point, which is 2 on the y. So we go from 0 to 2 of the top function, which is y plus 2, minus the bottom function, which is y squared, and all of that would be done now with respect to y. So that's another way to still come up with the same answer of 10 thirds. Okay? And there is even still a third way to work this problem out. And that would be to look at the entire area underneath the curve y equals x squared all the way up until that point. So we really have a region that looks kind of like, if these are our axes, it kind of looks like all of this, okay? And so that would be the integral from all the way from 0 to 4 underneath square root of x. But then what piece don't we want? We don't want this little triangle here. And so we would really then subtract the integral from 2 to 4 underneath x minus 2 to subtract that away. We could also just subtract the area of a triangle that we can see there, which has a base of 2 and a height of 2, and 1/2 of 4. We know that this integral's value is going to be 2. So another way to get our final answer of 10/3